good it feels.
That this is the pattern you would see. So specifically, if each word would sense in which using the list is cheating. And what makes for a more interesting puzzle and a richer information theory lesson is to instead use some more universal data, like relative word frequencies in general, to capture this intuition of having a preference for more common words. So, of these 13,000 possibilities, how should we choose the opening guess? For example, if my friend proposes weary, how should we analyze its quality? Well, the reason he said he likes that unlikely W is that he likes the long shot nature of just how good it feels if you do hit that W. For example, if the first pattern revealed was something like this, then it turns out there are only 58 words in this giant lexicon that match that pattern. So that's a huge reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word was equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000. Of course, they're not equally likely to be answered.
All right, hitting this pattern. So, all right, one thing I'm just thinking of now is that, okay, so behind the scenes, one of these words is chosen. Kind of, it's just like it's like the word of the day. Wagon. It's like the word of the day. And I guess in terms of, I don't know, guessing words that have common letters, so all these words are equally likely. I mean, they're going to pretty much have the distribution of like most common letters in words, just kind of like, yeah. So it's more likely that it has common letters. So if you kind of guess a word that starts with W, it's going to be less likely that you hit one of these words, it's going to be less likely that this winds up either gray, that this winds up either green, green or yellow. The most likely outcome, if you guess W, like in this first square here, is it's going to be gray. That's sort of like the most, common, it's the most likely outcome, let's say.
Most of these are very... flip side of that, of course, is that it's very uncommon to get a pattern like this. Words in this job likes the long shot nature of just how good it feels if you do hit that W. For example, if the first pattern revealed was something like this, then it turns out there are only 58 words in this giant lexicon that match that pattern. So that's a huge reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word was equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000.
Hitting this pattern.
Of course, they're not equally likely to be answers. Most of these are very obscure and even questionable words. But at least for our first pass at all of this, let's assume that they're all equally likely and then refine that a bit later. The point is, the pattern with a lot of information is, by its very nature, unlikely to occur. In fact, what it means to be informative is that it's unlikely. A much more probable pattern to see with this opening would be something like this, where, of course, there's not a W in it. Maybe there's an E, and maybe there's no A, there's no R, there's no Y. In this case, there are 1,400 possible matches. So if all were equally likely, it works out to be a probability of about 11% that this is the pattern you would see. So the most likely outcomes are also the least informative. To get a more global view here, let me show you the full distribution. Probably just the least informative.
It's just kind of weird because we've got two distributions going on here. I mean, so of these like 12,000 words, this is just each word here is the distribution here is uniformly random. Like you have an equal chance of guessing any of these words. So I'm just kind of struggling with this like two-step process where we pick a word and then we reason about the probability of getting that pattern. I feel like I need to look at this another way, like connecting this pattern to the number of words and the number of total possible words. I think I'm kind of getting confused because I'm kind of mixing up this pattern with kind of like selecting the word itself and like how likely this word is in comparison to other words. I mean, which is the same, but the letters in this word are going to be kind of more likely to be here. Because when I'm kind of seeing a pattern, I'm kind of not able to just reason about this kind of by itself. I'm kind of looking at all these other words as well. The pattern.
To get a more global view here, let me show you the full distribution of probabilities across all of the different patterns that you might see. So each bar that you're looking at corresponds to a possible pattern of colors that could be revealed, of which there are 3 to the 5th possibilities, and they're organized from left to right, most common to least common.
I'm kind of confused though. So this distribution here is indexed by like the actual word that's being chosen today, right? Like, so we like pick a W. So depending on the word that's chosen, you would get a different distribution, right? Maybe I'm going one step further than this right now. Than we're actually at. Maybe there is no word that's being chosen right now. We're just comparing different, what is he calling them? Color things?
Bar that you're looking formative. To get a more global view here, let me show you the full distribution of probabilities across all of the different patterns that you might see.
Patterns. So right now there is no like hidden word. It's just the full vocabulary, and we're looking to see for every single pattern, how much does that crunch down? How much does that crunch down the vocabulary size?
So each bar that you're looking at corresponds to a possible pattern of colors that could be revealed, of which there are 3 to the 5th possibilities, and they're organized from left to right, most common to least common. So the most common possibility here is that you get all grays. That happens about 14% of the time.
So how would we actually compute this? I guess we look at each of these words. So we just say, okay, let's find all the words with no W and no E and no A and no R and no Y. And so these are all disjoint too. So are they overlapping? Like, do these all sum to the vocabulary size?
And what you're hoping for when you make a guess is that you end up somewhere out in this long tail, like over here, where there's only 18 possibilities for what matches this pattern that evidently look like this. Or if we venture a little farther to the left, maybe we go all the way over here. Okay, here's a good puzzle for you. What are the 3 words in the English language that start with a W, end with a Y, and have an R somewhere in them? Turns out the answers are, let's see, wordy, wormy, and Riley. So to judge how good this word is overall, we want some kind of measure of the expected amount of information that you're going to get from this distribution. If we go through each pattern and we multiply its probability of occurring times something that measures how informative it is, that can maybe give us an objective score. Now, your first instinct for what that something should be might be the number of matches. You want a lower average number of matches. But instead, I'd like to use a more universal measurement that we often ascribe to information, and one that will be more flexible once we have a different probability assigned to each of these 13,000 words for whether or not they're actually the answer. The standard unit of information is the bit, which has a little bit of a funny formula, but it's really intuitive if we just look at examples. If you have an observation that cuts your space of possibilities in half, we say that it has 1 bit of information. In our example, the space of possibilities is all possible words, and it turns out about half of the 5-letter words have an S, a little less than that, but about half. So that observation would give you 1 bit of information. If instead a new fact chops down that space of possibilities by a factor of 4, we say that it has 2 bits of information.
What does?
It has is the bit, which has a little bit of a funny formula, but it's really intuitive if we just look at examples. If you have an observation that cuts your space of possibilities in half, we say that it has 1 bit of information.
So information is this kind of narrowing. There's how much information is in an observation. So we have an observation, and we can ask how much information does that observation provide? How much information is in that observation? How much information does that observation contain? It's kind of weird too, because you could just imagine a situation where the observation is kind of deterministic, and we just take an observation, and like each observation is guaranteed to be 1 bit. Each observation is guaranteed to have 1 bit of information, provide 1 bit of information, to give us 1 bit of information. But in this case, we don't know how many bits of information an observation is going to provide. We can take actions that want to give us the highest expected amount of information in an observation.
In our example, the space of possibilities is all possible words, and it turns out about half of the 5-letter words have an S, a little less than that, but about half. So that observation would give you 1 bit of information. If it's then that abilities as all possible words, and it turns out about half of the 5-letter words have an S.
So basically, like if we guess an S, that's 1 bit of information right there. Yeah, let's simplify this problem, I guess. Like instead of having the like 5-letter patterns, we could just choose a letter and we could say, does the word have this letter in it? And if we chose S, then we would either get yes or no. We either get yes. Yeah, yes, the word has an S in it. See, I'm kind of, wait, okay, keep going back and forth between like the word has been chosen versus the word has not been chosen, because in this case, like the word isn't chosen. We're just highlighting all the words that have an S. So you can imagine this gets toggled one way or the other depending on the actual hidden word. If the hidden word does have an S, then these are the words that are left, and that's going to cut down our space by half. If the hidden word doesn't have an S, then we're just going to get the inverse of this, or like the XOR of this, the XOR of this observation, I guess. The XOR of this result. The candidate words that are left are going to be the XOR or the inverse of this result. But in either case, it is going to cut down our space of possibilities by like a half.
But about half. So that observation would give you.
But I guess like if say only like a quarter of the words have a C, I guess. Let's say a quarter of the words have a C. So either the hidden word has a C or it doesn't. If the hidden word has a C, then yeah, like then that observation provided us 2 bits of information. But if the hidden word doesn't have a C, our space of possibilities only got cut down by only a fourth got taken away, only by 3/4. So that's less than a bit of information. So say, I don't know, maybe it's like 0.75 bits of information in that case. So we got lucky or unlucky. Yeah. Okay.
Bit of information. If instead a new fact chops down that space of possibilities by a factor of 4, we say that it has 2 bits of information. For example, it turns out about a quarter of these words have a T. If the observation cuts that space by a factor of 8, we say it's 3 bits of information, and so on and so forth. 4 bits cuts it into a 16th, 5 bits cuts it into a 32nd. So now is when you might want to take a moment and pause and ask for yourself, what is the formula for information for the number of bits in terms of the probability of an occurrence? Well, what we're saying here is basically that when you take 1/2 to the number of bits, that's the same thing as the probability, which is the same thing as saying 2 to the power of the number of bits is 1 over the probability, which rearranges further to saying the information is the log base 2 of 1 divided by the probability. And sometimes you see this with one more rearrangement still, where the information is the negative log base 2 of the probability. Well, what we're saying here is basically that when you take 1/2. space by a factor of
Bringing in
8, we say
probability
it's 3
now.
bits of information.
Oh, I kind of missed
Five-letter
this
word.
when we were.
And that cuts your space of possibilities in half. We say that it has 1 bit of information.
What is. Okay, I'm struggling to connect this to probability though. So he's saying this observation cuts your possible candidates in half, and this is the part where I'm still confused. He's saying like that has a probability of 1/2 of happening. Maybe the 1/4 would be easier to understand.
In our example, the space of possibilities is all possible words, and it turns out about half of the 5-letter words have an S, a little less than that, but about half. So that observation would give you 1 bit of information. If instead a new fact chops down that space of possibilities by a factor of 4, we say that it has 2 bits of information. For example, it turns out about a quarter of these words have a T. If the observation cuts of information.
Okay, so I think this is starting to make sense now. So I'd say, yeah, there is. So it does sound like there is a probability of 1/4 that your space of possibilities gets cut down by, not cut down by a factor of 1/4, but gets shrunk to 1/4 of the original size, because only a fourth of the words actually have a T, and all these words are equally likely. So the probability of this outcome happening I guess we could have a random we could have an experiment here, a probabilistic experiment, and the outcomes in our sample space are like the space of possibilities gets shrunk down to whatever, like a half or a fourth or an eighth or 3/5 or like 1/1,000 something. And these all have different probabilities associated with them. Half of your half of your words have an S, so the probability of your okay, I think I have a flaw in my reasoning, because so if kind of saying
is bit would give.
What I wanted to say was the probability of your sample space shrinking in half is 1/2, because half of the words have an S. But that's not true. The probability of your sample space shrinking by a half, if you guess S, is 1. Because if it has an S versus it doesn't have an S, it's 50-50 in both cases. So the probability of this thing happening is 1. You're certain to shrink it in half if you do that. But maybe he's kind of saying the probability of landing in this half in this region versus this region is 1/2. Maybe the same thing for the next one.
Bit of information. If instead a new fact chops down that space of possibilities by a factor of 4, we say that it has 2 bits of information.
Okay, so the probability of getting in this region here is 1/4. If you guess a T, then the probability of winding up in this region is 1/4, because all the other words are over here, and yeah. Okay. See you later. Peace.